Alright, this lesson is titled Optimization Problems. In this example, we're given a rectangular field that's fenced off along the bank of a river, and no fence is required along the river. If the field is to have an area of 1,800 square yards, what should be the dimensions of the field in order to require the least amount of fence? Let's make a little room here. Let's draw a diagram. There's my river, real nice and straight. My fence is going to go along the river something like this. I only need 3 sides. I don't know what those sides are, so I'm going to start labeling. The area is 1,800 square yards. That's what we're trying to get. I'm going to let the vertical distances here be x and the horizontal distance be y, just because. Therefore, the area of this region is going to be x times y, length times width is 1,800. And if I solve for y, y is just 1,800 over x. My fence, the amount of fence I'm going to need is 2 x's plus a y. Well, y is the same as 1,800 over x. So if I use 1,800 over x instead of y, I can write my function for the amount of fence I need just in terms of x. And x has to be greater than 0. I can't have 0 amount of fence and fence anything in. I'm going to find the derivative of this function f that represents the amount of fence. Derivative of 2x is 2. The derivative of 1,800 over x is negative 1,800 over x squared. Let's find the zeros and where that doesn't exist. It wouldn't exist at 0, but that's not in the domain of x, so we're not going to worry about that. If I set this equal to 0 and solve, I find that x can be 30. If I go to the second derivative of this same function, I get 3,600 over x cubed, which, when I plug in 30, is positive. In fact, for all values of x that work in this function, this will come out positive. If it's positive in the second derivative, that means that my function is concave up at any point along there that I would find, and therefore I have to be dealing with a minimum value because it's a 0 of the first derivative and positive in the second derivative. So my minimum is going to be when x is 30 and y is 1,800 divided by 30, or 60, or a 30 by 60 yard fenced area. Go ahead and pause this if you want to look at this longer. We're going to move on. Here's a U-try. We've given a box with a rectangular base whose length is twice its width. It's to have a closed top. The area of the material in the box is to be 192 square inches. What should the dimensions of the box be in order to have the largest possible volume? Go ahead and pause this and then try the problem, and when you're ready to check or look for a hint or whatever you need, press play. Okay, I need a little more room here. I'm going to draw a sketch here. There's my rectangular box. The area is to be 192. Go ahead and put that in there. That's my surface area of my box. What should the dimensions of the box be in order to have the largest possible volume? So I'm trying to maximize my volume here. Well, I don't know any dimensions, so I'm just going to create some here. It says that my length is twice the width, so I know nothing about the width. I'll go ahead and let that equal w. Therefore, my length is 2w. The height is unknown, so I'll put an h there. Surface area is 192. Surface area is basically just add up all of the areas. So I have the bottom and the top, the area that would be 2w squared. I have 2 of those. I have the ends, one here and one on the left. That'd be wh. There's 2 of those, and then I have the front and the back. There's 2 of those. That has to equal 192. If I solve this for h, I should be able to work the problem. H is the same as 192 minus 4w squared over 6w. I'm trying to maximize volume, so let's write a volume equation. Volume would be length times width times height. The length times width is 2w squared times the height. I don't want to use h. I want to stay in terms of w, so I'll use this value for h, which is 192 minus 4w squared over 6w. We can reduce a little bit. 2 goes into 6 3 times, and w squared over w leaves a w here. So that reduces it out, makes it a little nicer function. Let's find the derivative Or no, let's go ahead and simplify. Let's multiply by w over 3, so we don't have to deal with a product rule here. Now let's find the derivative. Derivative of 64w is 64. The derivative of 4w cubed over 3 is just 4w squared. Let's see where that equals 0. That equals 0 when x is 4 or negative 4. However, w can't be negative 4. We wouldn't have a box with a negative distance on one edge. And let's go ahead and look at the second derivative. The second derivative will be negative 8. When w is 4, that will be a negative value, which means we're concave down, which means we're looking at a maximum at the point where x is 4. And that's what we're trying to do. We're trying to find the largest possible volume. That'll happen when w is 4, L is 8, and the height, when we plug that 4 in here, we get 5 1/3. What should the dimensions be in order? I guess it didn't ask for the volume, it just asked for the dimensions. So there we go. Go ahead and pause here if you want to look at this longer. Here's another example. Consider the problem. A farmer with 750 feet of fence wants to enclose a rectangular area and then divide it into 4 pens with fencing parallel to one side of the rectangle, not sided, side of the rectangle. What is the largest possible total area of the 4 pens? Well, let's draw a sketch here. It doesn't say that the pens are the same size, so I'm going to make 4 pens that aren't uniform. I know that I have 750 feet of fence. I know that this dimension will equal that dimension, so I'll call this y, and these vertical dimensions I'll call x. I know that the perimeter, or the amount of fence I'm going to use, is 5 of these x's and 2 of these y's. That has to equal 750. And from that I can find that y is the same as 750 minus 5x over 2. We're looking for total area, largest total area. Well, area is just length times width, or x times y. But y is 750 minus 5x over 2. This keeps me in one variable. If I distribute the x, I don't have to worry about the product rule. Let's go ahead and find the derivative. Derivative would be 375 minus 5x. If I set that equal to 0, I get 75. The second derivative of this guy would be negative 5, which means this is always concave down. It doesn't matter what value I found here to plug in. It's always going to be concave down. I'm always going to be looking at the max. So whatever 0 I found in the first derivative is going to give me a max. That's when x is 75. When x is 75, y is 187.5. 75 times 187.5 gives me an area of 14,062.5 square feet. That's my maximum or largest possible area. Here's one for you to try. A piece of wire 10 meters long is cut into 2 pieces. One piece has been into a square and the other has been into an equilateral triangle. How should the wire be cut so that the total area enclosed is A, a maximum, and or B, a minimum? Go ahead and pause the video here and give that a try. Let's see. Let's try to draw this. Here's my wire. It's 10 meters long. I'm going to cut it somewhere between one end and the other, I would guess. And then I'm going to take one end and bend it into a square, and take the other end and bend it into an equilateral triangle. I don't know how long these are going to be. I don't know where my cut's going to be. But if I cut it here, that means I've got x divided by 4 for the length of each side of my square, and I've got 10 minus x left of wire here. If I divide that by 3, that's the length of this side of each side of my triangle. I'm trying to find a maximum and a minimum area. So let's look at areas. The area of my square is just x over 4 times x over 4, which is x squared over 16. The area of my triangle, if I look at this perpendicular, it's going to give me a nice 30, 60, 90, because remember it's equilateral, so it's also equal angular. So this is 60. Cut it in half, I get 30, and I have the 90 here. So it'd be 1/2 base, which is the whole base here, is 10 minus x over 3 times height. Well, the height would be half the hypotenuse times root 3. Half the hypotenuse is 10 minus x over 6 times the root 3. And so there's my function. Let's see if we can clean that function up a little bit. I realize that the cut distance here, x, has to be somewhere between 0 and 10 inclusive. I guess if I don't cut it at all and I make all of a triangle, or if I decide I'm not going to cut it at all over to this edge and I make all of a square, those are two possible solutions, the endpoints of the domain, if you will. We'll go ahead and find the derivative of the function. And simplify that derivative a little bit. We just reduced a 2 out of here with a 36 in the bottom there. And then set that equal to 0 and solve. If I multiply both sides by 72, I can get rid of these fractionals, the 18ths and the 8ths. I come down to this polynomial. Distributing the 4 root 3 and solving for x. I get this nice value for x, 40 root 3 over 9 plus 4 root 3. So x is approximately 4.35. Now I just need to see which one gives me a min, which one gives me a max. So I basically have three choices. If I don't cut it from the left side, I'm going to make all of a triangle. If I don't cut it from the right side, I'm going to make all of a square. And if I cut it when x is 4.35 meters, I'm going to make a triangle and a square. So let's see what we get. If I don't cut it from the left side, I put in 0 for x into my area function, I get about 4.81. If I don't cut it from the other side and make all of a square, I get 6.25. And if I cut it at the 4.35, I'm going to actually use the exact value here so I don't round twice. Plug that in into this function on my calculator, I get about 2.72. Therefore, the maximum occurs when x is 10. In other words, I make all of a square, use it all to make a square. And the minimum occurs when x is about 4.35 meters. Go ahead and pause here and study that for a little bit. Just another example. A woman at point A on the shore of a circular lake. How many circular lakes have you seen? With a radius of 2 miles, wants to arrive at point C. So she's at A, she wants to be at point C. Point C is diametrically opposite, in other words, on a diameter, opposite A on the other side of the lake. She wants to get there in the shortest possible time. It turns out this lady can walk at a rate of 4 miles per hour, and she can row the boat at a rate of 2 miles per hour. The question is, how should she proceed so that she can get from A to B the fastest? Should she just row all the way to C and then walk to B? Should she just start at A and walk all the way to B? Should she form some angle between A and B and C here, and then just take the boat into this area and then walk up? We have to figure that out. So I'm going to let R be the distance she rows and W be the distance she walks. And again, this walking distance could be from A straight to B. We wouldn't go this way. That wouldn't be the fastest. Okay? Rate times time equals distance. Therefore, time equals distance divided by rate. If she rows all the way across, so she just starts here and rows all the way across, we could figure that out. It'll take 2 hours. Actually, she's going to point C, so I'll take that back. She's going to point C. That's what would take 2 hours because she goes at 4 miles an hour. She goes at 2 miles an hour, so it would take her an hour to get to the center and another hour to get across. So there's our 2 hours. If she walks all the way around, so she's going to walk from here all the way to C, we could figure out the circumference of the circle and figure out how long it would take her to go that distance. It would take pi over 2 hours to do that. If she rows part way and then walks the rest, we need to figure that out. It will take R over 2 plus W over 4 hours. Time is equal to distance divided by rate. Okay? The time that she rows would equal the distance she rows, R, divided by the rate she rows, 2 miles per hour. Plus the time that she walks would equal the distance she walks, W, divided by the rate she walks, 4 miles per hour. W is the same as 4 pi, or excuse me, 4 theta. Cosine of theta is equal to r over 4, where r equals 4 cosine theta. So we've solved for r, and we've solved for w. We can plug these back into here. We can go over in class how this works. Theta has to be somewhere between 0 and 90 degrees, or 0 and pi over 2. It would make sense to go out this way somewhere. She's going to want to go across the lake. She can't row out into the field or whatever that is. So the total time is equal to r over 2 for cosine theta over 2 plus w over 4, which is 4 theta over 4. If we get a common denominator, actually we just reduce here and reduce there. 2 cosine theta plus theta is the time it would take. If we take the derivative in terms of theta, then negative 2 sine theta plus 1. If we set that equal to 0, we find out that theta has to be a half, or sine of theta has to equal half, and theta is 30 degrees or pi over 6. So when t is 0, it'll take us 2 hours. When t is pi over 6, it'll take us 2.26 hours. And when t is pi over 2, that's walk and all the way, it'll take 1.57 hours. So she should walk, and she'll get there the fastest. Again, we'll spend some time in class going over how we got this W and this R, all right, if you don't see that. Go ahead and pause here if you need to. That's our learning target for this lesson. I'll see you in class.